Okay, now this is where it gets fun. And by fun, I mean tedious. So, by fun, I mean please connect mouse. There we go. Okay, I made up some data. Don't worry about data, don't write them down. Okay? I'm just a hypothetical experiment. Say you're collecting data on the effects of retention interval on memory. And for the people in here who aren't psychologists, retention interval is the time between study and test. That's all it is. So if I give you a list of words, which is what this is all about, and then I have you wait a certain amount of time, and then I test to see if you remember the words. Okay? So, and I might use a percentage correct as my dependent variable. And I have 5 minutes, 1 hour, 24 hours. What's your percent correct? It's going to be about 5 minutes, would be about 90. And then an hour and 24 hours will be almost close to indistinguishable. That's real. Those aren't real data, but that's what the data would look like. Okay, so if I gave you probably 20 words, you'd be able to recall. If we had recognition, recognition would look like that. Recall wouldn't be quite that good. Don't make this your honors thesis. Ebbinghaus figured this out in 1880. So this isn't something you want to do now. So you know that. You conclude that RI, retention interval, affects memory. Yeah, you did. Way to go. You replicated something that's been replicated 1,000 times. Nothing wrong with replication. And it's a completely reasonable thing to do. This is the kind of thing you might do in a psych lab class or something. Okay. What if you, instead of using retention interval, here's another possible independent variable, levels of processing, low, medium, and high. So levels of processing, a low level of processing, and to learn more about this, take my memory course next year, which apparently is scheduled in the fall, which it shouldn't be. I don't know. They just do things, anyway. So it might not be my memory course, maybe somebody else will teach it. Because apparently I'm scheduled to teach 85 courses in the fall. There's no way I'm doing that. So, anyway. A low level of processing is looking at the surface features of a word. So I would count the number of ascending and descending letters. So for what, with the capital W, I've got one ascender, two ascender. I guess the T would probably count normally, so that's 3. I would give you a number. So I would show you the word, and you just count the number of ascending and descending letters. All you have to do is look at the way it looks. And I'm showing you these pretty quickly. Like every 3 seconds I'm showing you a word, and you just give me a number. A medium level would be looking at some acoustic characteristic of it. So I ask you how many syllables are there. Okay? And then you reply with a number, which is quite nice. Okay? So I can get you to reply to the same way, but you're processing it at a medium level. At a high level of processing, you're actually thinking about the meaning of the word, and I would get you to rate the pleasantness of the word on a scale from 1 to 7. Okay? And then we can look at recall or recognition or whatever, and you would get something to that effect. The deeper the processing, the better something is remembered, and you would know this even if you're not somebody who's anything but cognitive psychology, or I'm not even a psych major. You will know that if you think about material when you're studying and put it in your own words, you do better than just trying to memorize it just because of the way it looks. Just looking at a diagram going, okay, doesn't help a whole lot. You can learn that way, just not as much. Sure, so you find that levels of processing affects memory, which is not, again, an earth-shattering result. But it would happen. You'd get a nice solid result. So you say levels of processing affects memory. Probably the most cited paper in experimental psychology is a paper by Quick and Lockhart in 1972 about levels of processing from the University of Toronto. Great. Now there's a question you might be thinking to yourself, and that's what level of retention interval, what retention interval should you use for the levels of processing experiment? 5 minutes, 1 hour, 24 hours, 2 weeks? I don't know. And conversely, what level of processing should you have done the retention interval experiment at? So would you have done it with read the word and think about its pleasantness, or would you do it with count the number of ascending and descending letters? Would you use the, how many syllables are there? So it's actually a reasonable question to ask those. Those are two pretty reasonable questions. What about combining them both into one mega awesome experiment? Why, yes, we will. So you combine the two, and you get the G's mean groups: group 1, group 2, group 3, group 4, group 5, group 6, up to group 9. This is levels of processing on the left. This is retention interval along the top. So now we have 9 groups of subjects, independently assigned to different conditions, to different levels of retention interval and level of processing. Does that make sense? Right? And I think you've all dealt with something like this before, a factorial ANOVA, or this would be a 3 by 3 analysis of variance. But I think you've all dealt with it before. You've dealt with this before, even if it's just theoretically, you've dealt with this, eh? Okay. Now, we need a structural model, because everything comes out of the model. Once we make a model of something, we can then figure out how to analyze the data. So here's the model. Whoa, that was weird. I kind of like that. X equals mu plus alpha plus beta plus epsilon. And I'm sorry, those alphas and betas are not about type 1 and type 2 error. It's really annoying. I hate the discipline sometimes, right? I hate statistics sometimes. And this is one of those times because I've been talking about alpha and beta, type 1 and type 2 error, and now that's not what those mean. Those mean levels of A and levels of B. A and B are the different independent variables, okay? It's annoying, but it's also just life. So there are different alphas and betas. Do you like that? So any score, that's X, equals the grand mean. I was playing with all the transition effects. I get bored. The A effect, the B effect, wish there was a star wipe. There must be. And an AB interaction, plus, of course, error. A score equals the grand mean, plus alpha plus beta, A effect, B effect, plus alpha, beta, plus epsilon. So in a lot of respects, this is no different than the model that we had for the one-way ANOVA, which is X equals mu plus tau plus epsilon. Tau is levels of treatments. We just have two kind of tau kind of things, two treatments now. We've got A and B, right? We have A and B. We've also got this new weird thing, this wacky, zany alpha beta dealio. We'll talk more about that in a sec. But the point is, we got A effect, B effect, AB interaction, error. Okay? Questions so far? Other than how can I do those awesome transitions and fly-in effects on my computer? Yes?
For the A and B interactions, just like them multiplied together? Or whether like...
Yeah, it looks like that, doesn't it? Kinda. Yeah, it's not exactly that. That's we'll see the second one is, and it looks like a multiplicative factor.
Yeah.
It isn't quite that.
Okay.
I know, that's very annoying. It's a good question, too. Other question. Okay. So, let's explain this a bit more. So, not only can we look at the A and B, right, so we look at both A and B, and the effects of those independent variables, what levels differ from each other. So that's just like, in the assignment you just did, you had just one variable, A, and it had 4 levels, 4, so in one day 4. This one now is going to have A and B. Okay, so both of those. So we can look at those. We can also look at how A and B act together, or how they interact. Okay? It's kind of a whole is more than the sum of its parts kind of deal. It's like, Biology students would be very familiar with the interaction principle, the idea that things are, genes and environment interact. It's like that. It's like, I don't know, if we could somehow measure natural ability at something. What are we going to measure natural ability at? Hockey. So, yeah, let's just, we're not think how we're going to quantify hockey ability, but let's just pretend. We're going to measure natural ability in hockey. Let's see if we can do that. And we know that the better you are, is like, there's something that's built in, something from your parents or something. And then there's also practice effects. Right? So if you practice, you're going to get better. But if you practice a lot and you've got some natural ability, you'll be really good. And that's over and above just practicing and just being a natural athlete. Right? So there's always those great stories of thinking back. I think back to stories of Wayne Gretzky practicing playing hockey till he was like, he was 4 years old. He's out of his backyard rink till his the sun goes down. There's Sidney Crosby destroying his mom's dryer by shooting pucks into it when he was 5 years old. Right, so there's all these stories. These guys are already really good, naturally gifted people. They also practice a lot. There's pretty something there. That's the interaction thing. It's over and above the additive effect of the level of A and level of B. It's what's left over. There's something else there. It's A and B together. I could make a depressing version if you don't understand that there's also a depressing analogy I can make. But did you understand that analogy? Because if that makes sense, I don't have to be depressing. Are you good? Is everybody good? You understand what I'm saying? It's over and above the additive part. Because the depressing one is about racism and sexism, so that's... Okay. So you're okay. Good. So I don't have to use the depressing example. Here's a happy example for a change. I've been for years trying to think of a happy example because I always use this. It's harder to be a woman of color than it is to be a woman or be a person of color. And it's like, then we all go, let's pretend it's all about hockey. So now I've given you the depressing one example anyway. Both sides. Okay, so it's the effect of one variable changes depending upon the level of the second variable. The effect of one variable changes depending upon the level of the second variable. That's what an interaction is. The effect of one variable changes depending upon the level of some second variable. Okay. Oh, here we go. I don't know what I'm measuring for my dependent variable here. All I know is this is B1, and this is B2, and this is A1, this is A2. And look, the effect of B is smaller at A1 than it is at A2. The effect of B changes depending upon the level of A. Does that make sense? Now when you see it. The difference between B1 and B2 is smaller at A2 than it is at A1. No, smaller at A1 than it is at A2, it should say. Oh, worst. Okay? Very tired, I'm sleeping. Got up at 5. Can't wait for this break. I'm sure you'll feel the same way. Good, Cheyenne, a question?
Yeah, it says the difference between B1 and B2 is smaller at A2 than at A2?
Yeah, it should say smaller at A1 than it is at A2.
Okay.
Yeah.
So this is like predisposition plus environmental factors.
Same sort of idea, yeah. So there's like environmental factors, there's genetic factors, but
Together.
they do something else as well.
Okay.
Yeah. And that's still even kind of, because of the way genes work, pretty simplistic. But, yeah. Yeah, exactly. Shouldn't be over the top of that. It looks horrible. The effect of B changes depending upon the level of A. Doesn't it, right? The effect of B is small at A1 and big at A2. Questions? Good? Okay. I know you've all seen this before, maybe in 2127, or maybe in 2126, or maybe in whatever that biology stats class is called. Right? I think you've all seen it before? Okay. So, x equals mu plus alpha plus beta plus alpha, beta plus epsilon. Or, if you want to think about it, x equals mu plus a plus b plus ab plus e. If you want to think of it that way, but they aren't, Roman letters, Latin letters, they are Greek letters. Alpha and beta are the first two letters of the Greek alphabet, which of course is where we get our word alphabet. This is usually where someone goes, whoa, I never thought of that. Yeah, that's true. Okay. So we have assumptions. We have assumptions about the model. First assumption is that this is okay. Sum of the alpha i's equals 0. That means how much each level, whatever you are at A, if you're in, let's say, A1, your score goes up 2. If you're in A2, let's say we have 2 levels, your score must go down by 2. They sum to 0. So the effects, the A effects, what are called the simple main effects, for A, so let's say we just have A1 and A2. Simplest possible design would be what's called a 2 by 2. A1, A2, B1, B2. So I can draw this out here. So we have 4 groups, right? 1, 2, 3, 4. Being in A1, let's say it raises your score by 1. That means being in A2 decreases your score by 1. Okay? Before it was the case, I don't think I mentioned this, maybe I did, with the one-way ANOVA, some of the treatment effects must equal 0. You probably can figure out that the sum of the beta j's, these are just 1, 2, 3, 1, 2, 3, that's what i's and the j's mean. So the betas go up by, if they go up by 2, they must go down by 2. Okay? So as the sum of the treatment effects for B must also sum to 0. And you might say, Dave, you're putting a hell of a restriction on this. You'll see in a second when we break this down, go the other way, when we break it down, that, I'm pretty good at this, that it can't not work like this. This happens because of the way the model works. You'll see it in a second. If you don't see it already, you will see shortly that it just works like this. The sum of the alpha I beta j's, now this is the individual A1, B1, A2, B1, A1, B2, A2, B2, must also sum to 0. So like plus 1, minus 1, minus 1, plus 1. They have to sum to 0 both this way and this way, both horizontally and vertically. And you'll see again in a second that they can't not. When we go backwards, we break everything down, you'll see that it cannot work that way. There's no way that it could be any other way. Think about this. These are all just deviations from the mean. That's what those effects are, right? They're just deviations from the mean. And deviations from the mean, when we're doing sums of squares, must sum to 0. They have to. Error is normal and independent. So each individual individual difference is normally distributed. They're independent of each other. They have a mean of 0 and a variance of sigma squared sub epsilon. Questions? Okay. So, there's also, we're going to eventually do an F test. In fact, we're going to do 3 F tests. So there's going to be assumptions about F. F says we have homogeneity of variance, that all the variances are equal. We're used to that. That we have random samples. Yeah, sure we do. That's not a big deal. we can violate the hell out of that. We can violate homogeneity of variance to a point that the S rule of thumb is about 4 times, and that's about right. Normal populations, doesn't matter. We can violate that. I mean, the good thing about it is the math originally said, oh, you have to have all these things, but then when you test it, it's like, it's not that important. And of course, independent events, which you cannot violate. Okay. Numerical, well, I said before that the error was normal and independent, meaning all of your individual differences are independent. That's where that is taking you to by now. Okay, let's take a look at a numerical example. I don't know what we're measuring. I don't know what the experiment's about. I have no creativity. My wife is a visual artist. My brother is a Grammy-nominated record producer. My sister is a commercial artist. I have literally no creative ability whatsoever, except I can now and then design kind of clever experiments. So I don't know what this is an example of. But we have 2 levels of A, 2 levels of B, and some dependent variable. I don't know what I'm measuring, and I don't care. The numbers don't know where they come from. So, but these are means. We're going to think of these as group means, okay? So 9, 7, 3, and 1, they're group means. They aren't actually individual scores. So I don't even know how many people are in each group. We're not even going to think about that. This is more conceptual. Remember, x equals mu plus alpha plus beta plus epsilon. Right. Well, let's take things out of here to see if we can get the individual values for these different quantities. So let's find the grand mean, that's mu, and just remove it from every cell. Well, the grand mean, 9 and 7 and 3 and 1, that sums to 20 divided by 4 because we have 4 cells, is 5. So now we're going to take 5 out of each cell. Okay? Questions so far? Good? Okay. Take 5 out of each cell. So if we're going to take 5 out of here, we're going to get 4. Take 5 out of here, we're going to get -2, etc. Yeah, 4, -2, 2, -4. So with the grand mean removed, now we can go on to the effects of A and B. So I've taken the effect of A out. Or sorry, of the grand mean is gone. If the grand mean's gone, by the way, everything should sum to 0 now. Oh look, 4 plus 2 minus 2 minus 4. Oh, it's 0. Cool. So now we're going to take the effect, the B effect out. So I've summed across A, 4 and 2 is 6, -2, -4, -6. I'm going to divide it by 2, so it's going to be 3 and -3. I'm dividing by 2 because there are 2 observations. It's just a mean. The numbers don't know where they come from. It is a mean of means, but the numbers don't care. So B1 is 6 divided by 2, which is 3. B2 is -6 divided by 2, which is -3. I'm now going to remove 3 from all the B1s and remove -3 from all the B2s. Okay. By the way, you know this. Now we have these are deviations. We took it from 0 We took the mean out, so they're in essence deviations from the mean. There's sums of squares. If we squared these, 2, that'd be the sum of these squares. So the sum of squares for b is 18. 3 squared plus negative 3 squared. So take 3 out of b1, take negative 3 out of b2. So we end up with 1, negative 1, 1, negative 1. So we get 2 and negative 2 for a1 and a2. a1 is 1. a2 is negative 1 because we divide by 2. So now we're going to subtract 1 from all the a1s and subtract negative 1 from all the a2s. So the same thing as we did before, but now for the a's. So we take 1 out of here, take negative 1 out of here. Nothing. We have nothing left. That tells us there's no interaction. Right? There are just effects of A and B. There's no interaction. If these were non-zero, we'd have interaction, but they aren't non-zero. They are 0. They aren't non-zero. They are 0. Bit of a feel already. It's cold today, right? Suddenly reminded that we live in Northern Ontario today, aren't you? Oh, it's minus 22. Great. It's almost that temperature you wake up and go, I wonder if the pipes are frozen. But not quite, but 10 degrees colder. But it's when you walk out to go to the bus and you think, oh, this is nice. It's brisk. This is wonderful. My God, I'm in hell. Like it takes very quickly, you have that feeling like what a nightmare this is. So the sum of squares for A, by the way, would be 2, right? Because it's 1 squared plus negative 1 squared. Sum of squares for AB would be 0. This never happens. It would never be 0. There would be something there. In fact, if it was a 0 there, I'd probably think you made up your data. Like I just did. Okay. Questions so far? All right. That's a good little rest sitting down here. Oof. So if we graph it, you can actually see there's no interaction. Right? The lines are parallel. So we've got, here's the 2 scores for, that's for B1, that's for B2. We see there's no interaction, that the effect in A doesn't change depending upon the level of B, or vice versa. Right? Good? Okay. Questions? Do you have any questions for me so far? Okay, good. Let's do another one. This is so much fun. Again, I don't know what they are. We got 20 minus 10, 0, 2, blah, blah, blah. Take a quick look at this. The difference between A1 and A2 at B1 is 20, and at B2 is negative, well, that's just the size of it overall. 12. So there's probably going to be an interaction here because the effect of A changes depending upon the level of B. Just looking at that, you should be able to see there's probably something going on. Okay. So, first get the grand mean. 20 plus 0 minus 10 plus 2 divided by 4 is 3, so it's 12 divided by 4 is 3. So we take 3 out of all these. Excellent. So let's remove that grand mean. And we get 17 minus 3 minus 13 minus 1. And we're going to sum across the b's to get the a of x. So the sum is 4 and negative 4, so it's 2 and negative 2. We're going to take 2 out of all the a1s and take negative 2 out of all the a2s. By the way, if you forgot and you were afraid to ask about why negative, like, you took out -2, and it's like adding, remember you take out negative, it's like you're adding. Right? Stuff you learned in like grade 7, you forgot why you were negative numbers. Okay. So also these always sum to 0. And that's not because I cooked the example. The only way I cooked this example is I did it so that it always be whole numbers, there's no fractions. There's no fractions. But everything else, you could use any 4 numbers you wanted to. It would always work out this way. It just works. So while you say it's an assumption of the model, the math has to work this way. It must. It must. Okay. And also these now sum to 0 because we've taken out the grand mean. Cool. Take 2 out from A1 and A2. And -2 from A2 rather. We had 15, -1, -15, 1. So it's 14 and -14, so it's 7 and -7. Columns sum to 0 because we've taken the effect out. The total sums to 0 because we've taken the whole thing out. This doesn't sum to 0, the rows yet, because we haven't taken that out. We will when there's 7 and -7. Right? So let's take 7 out of B1 and -7 out of B2. And we end up with this. Oh, there's leftover stuff. There's an interaction. And now I can tell you what's the sum of squares for interaction. It's 256. Because it's 64 plus 64 plus 64 plus 64. 8 squared plus -8 squared plus -8 squared plus 8 squared. Right? Okay. The effects actually sum to 0 in all possible ways. This is very cool. All together they sum to 0 across and also up and down. You don't do diagonally. Okay. So far, do you have any questions so far? You're good so far? You already thinking about the break? Is that what you're doing? A lot of you, this is your last class before the break, and you're thinking, I don't have to go to school for like a week. Me too. Me too. Believe me. Okay. I'm going to play so much Civilization. That's all I've been doing, playing Civ 6. It's kind of sad. That's all I think about. If it was just zeros, we'd say there's no interaction. But it's non-zero, so we definitely have an interaction. If you graph that, you can see the effect of any change depends upon the level of B. If the lines cross. If the lines are crossed, you got an interaction. Okay. Questions? So I graphed this up. Pretty easy to see we have an interaction. It's pretty obvious that the effect of one variable changes depending upon the level of some second variable if the lines cross. Okay. So how do you interpret an interaction? It's easy to interpret a main effect to say that, so if there's an effect of, then we're going back to rotation, everybody say, well, as time goes by, you get poorer at memory. Or as level of processing increases, you get better in memory. Those are pretty obvious things. But what would it mean to say there are levels of processing by retention interval interaction? You're saying the effect of retention interval changes depending upon the level of processing, but how? So, if you're interpreting main effects, that's just the effects on their own, and the A's and B's without thinking about the interactions, It's a little harder to do in the presence of interactions than it is without the presence of interaction. When you have an interaction, if I say A1 is always bigger than A2, yeah, A1 is always bigger than A2. And then I say, but there's an interaction. A1 is always bigger than A2, except it's a little smaller at B1. It's like, that's a little clunky. So it's harder to do when there are interactions. If you have what's called an ordinal interaction, that's where the order of the main effects is preserved. So something like, let me draw a picture. Let's draw a picture of an ordinal interaction. Looks like this. Here we go. I'll take a picture of this and put it on internet. But you can see that A1 is always bigger than A2, but the effect is more pronounced at B2 than it is at B1. That's called an ordinal interaction. So I can confidently say that A1 is bigger than A2. I don't have to throw in a caveat about B. I don't have to say, depending, unless if B1 is here, then it doesn't work that way anymore. I can say that, yeah, at B2 the effect is bigger, but I can feel comfortable talking about the effect of A on its own. Okay. Now, a disorderly interaction, it's harder, if not impossible. So if I had something look like this, yeah, B2 is bigger than B1. Because B1's here, B2's here. Except the lines cross. So it's kind of, I can't really say, so this is called a disordermal. This is when the order of main effects is not preserved. So when the order of effects is not preserved, I have real trouble talking about main effects at all. They may exist statistically, they actually be statistically significant and all that stuff, but how can I talk about them on their own? I can't. Some people will tell you, never talk about main effects whenever there's an interaction. I think they're a little bit, I think that's silly. I will, however, say don't talk about main effects when there's a disordinal interaction. I'll say that, yeah, for sure. That's crazy. That's crazy talk. Questions so far? So the other day when we talked about the one-way analysis of variance, the simple analysis of variance, we talked about partitioning the sums of squares and degrees of freedom. Let's do the same thing for this kind of design. So what we have here, the model says x equals mu plus alpha plus beta plus alpha beta plus epsilon. That means we have a sum of squares for A, a sum of squares for B, a sum of squares for AB, and a sum of squares for error. Okay? And a sum of squares total. Okay? And then they're all going to split off and have to keep their requisite degrees of freedom with them. So sum of squares total equals sum of squares A plus sum of squares B plus sum of squares AB, plus sum of squares error. And each of these has a certain number of degrees of freedom. And there's a total number of degrees of freedom in the model. I'm sorry in the design. Ugh.
What was that last part you said?
What I was writing?
No, the degrees of freedom.
Okay, so there's a total number of degrees of freedom in a design, sum of squares. That goes with sum of squares total. Each sum square calculation has a requisite number of degrees of freedom. It has degrees of freedom to go with it, and they should all also sum to the total sum of degrees of freedom in the model. Remember, it was like k minus 1 plus n minus k actually equals big N minus 1, like in a regular ANOVA. The same thing's going to happen here. We're going to have big N minus 1 total, and then we're going to have a certain number of degrees of freedom for each of these.
Oh, okay.
Yeah. So, we got sum of squares for A. We got sum of, and that's the squared deviations of, let's call them the column means. Do I actually make that the column? Oh, good, I've erased it so I can't tell. Let's say column means from the grand mean. Sum of squares for B is the squared deviations of row means from the grand mean. And we were playing around before, when we took out the grand mean, it's from 0, it just makes doing it. If it's easier to get grand mean out. So that's those two. And they're just like sum of squares treatment. We do it twice. And then we've got sum of squares for AB. They're the squared deviations of cell means from what we would expect to get just from the row and column means. So we take the row means, the row effect, add the column effect, and look and see, oh, is that different from what we have for what we actually measure? Is that different? Squared deviation from that. And of course, sum of squares error is the sum of squares of individual scores from the cell mean values. Each, like A1, B1 is a cell, A2, B2 is a cell, etc. Okay? And that's our individual difference measure. Oh boy. So more precisely, you're never going to have to calculate this, so don't worry about it. But what I want to show you here is we have the total, which is x minus x bar sub g, that's the grand mean, squared. That's the total sum of squares. Row means from column mean, from grand mean squared. Column means from grand mean squared. Individual score minus the column mean, minus the minus the row mean, plus the grand mean. What? We've taken the grand mean out twice, actually. If we've taken it out twice, if we have the column mean and the row mean, so we just add it, put it back in. That's all that's happening. That's our interaction term, and then finally that's our individual difference score here. Okay. There's going to be n minus 1 degrees of freedom in the model. And those are A and B minus 1, levels of A, levels of B. So with a 2 by 2, it's just 1 and 1. Because there's 2 levels of A, minus 1 is 1. 2 levels of B, minus 1 is 1. If we had a 3 by 3, this would be 2 and 2. This is our interaction term. It's A minus 1 times B minus 1. That's big. That's pretty cool. And for error, it's A times B times N minus 1. Levels of A times levels of B times number of subjects in each group minus 1. Because remember, it's like we've got 4 little experiments, let's say, in a 2 by 2. So we have little n minus 1 in each one, and how many of those cells do we have? Well, A times B. Right? And if you take A minus 1 and add B minus 1 and then add A minus 1 times B minus 1 and then add in A times B times N minus 1, A times B times A minus 1, you add all those up, you get big N minus 1. I can do that, but I'm not going to. All right? So that's what we do, and we eventually end up being able to do what are, in fact, three different F-tests. We're going to do one for A, we're going to do one for B, and we're going to do one for AB. So we're going to find out if there's a significant A effect. We're going to find out if there's a significant B effect. We're going to find out if there's a significant interaction. All right, so you have to actually do three statistical tests in one analysis of variance. But that'll tell you if there's a significant A effect, a significant B effect, or a significant interaction. Questions? Do you want to go early because the break's coming? Mm-hmm. I do too. Let's stop now. We'll continue talking about this after the break. Thanks, everybody.
What are the significant effects? The A effect, the B effect, and what?
So, if you're watching this video on YouTube, a week-long break didn't just happen. But if you're not, in other words, if you're in this room, we did have a break. But last time I was talking about how basically how to calculate sum of squares A, sum of squares B, sum of squares AB. Hey, if you wanted to do it by hand, which nobody ever does. Okay? I'll show you how to do it with SPSS. It's really pretty straightforward. Might show you that today, maybe next time. Point is, it really just involves having different variables. So let's say A and B, and having different levels of A and B, 0 and 1, 1 and 2, doesn't matter. And then having a kind of variable, it's really pretty straightforward. That's how you set up the data set. So one of the things that I looked at, or we looked at, I guess, when we talked about the straight ahead analysis of variance, the univariate case, well, not univariate, but that's the wrong word, the one-way analysis of variance, is we looked at the expected values for mean squared treatment, mean squared error, and we saw that if we divided one by the other, we can isolate treatment, remember? Well, let's do the same thing here. Okay, so for the simple ANOVA, the expected value of mean squared treatment is epsilon plus tau, and I know it's actually sigma squared sub tau plus n times sigma squared sub epsilon. Let's say next epsilon plus tau is fine. And we divide by mean squared error because the expected value there is epsilon. And if I find out to put this stuff here, I will be mad. And I want to get it down. So we divide mean squared treatment by mean squared error. We isolate the treatment effect and find how big it is. So let's do the same thing here. But we have to do this for mean squared A, mean squared B, and mean squared AB. And for mean squared error, of course. So the expected value of mean squared A is alpha plus epsilon. Sigma squared sub alpha plus, you know what I'm saying. And for B, it's not surprising, it's beta plus epsilon. Again, this shouldn't surprise you. And AB is alpha beta plus epsilon. And of course, error is epsilon. So you can see there that to isolate the effects we're interested in, which are alpha, beta, and alpha, beta, we're just going to divide each of those by mean squared epsilon. Mean squared error. Right? Does that make sense, everybody? You good? Okay. So we're just going to divide by that. All right. Questions? Everybody okay? All right. Good stuff. Okay, then it gets complicated. There's always a however, isn't it? Those expected values are only true if those are the only values of A and B you're interested in. So in other words, if those levels of A and B, that's, well, 1 and 2, or let's say it's male, female, that's easy. Or let's say it's low and high levels of processing. Or let's say it's 5 minutes and 1 hour of vacation period. Any of these things. Is it really the case though that you're only interested in those levels? And as a rule, no, that's not true. You want to make inferences about what's between those levels as well, right? You really do. However, when you are only interested in those levels, that's called a fixed effects model. Okay? What if we randomly chose the levels? So instead of actually picking them, we put all the possible levels into a hat and drew 2 or 3 or 5 or whatever. Okay. Then we get what's called a random effects model. Now, why would you do such a thing? Well, you likely wouldn't do it in the kind of work that any of us would be interested in doing. You might do it if you were doing some kind of field work and you had access to a lot of, no, you probably wouldn't. I think the book has an example of looking at tire wear in different cities or something like that. They randomly choose the cities. Or I don't know if that's this book or another one. It's been so long. I don't read stats books very often. I like statistics. I don't read the textbooks for fun. That would be weird. So if we randomly chose it, the expected value of mean squared A is actually alpha plus alpha beta plus epsilon. And the expected value for B, mean squared B, is beta plus alpha beta plus epsilon. See, the interaction term gets thrown in there as another source of variation in the expected value of mean squared. The expected value for mean squared AB is alpha beta plus epsilon. And the expected value for mean squared error is epsilon. So this is, the math changes. You're thinking, well, what do you mean? How does that, you're always saying that if the numbers don't know where they come from. No, they don't, but you've added an extra bit of randomness into this, and we have to account for it. And that extra bit of randomness changes what the expected values are. Does that make sense? And if it doesn't make sense, just take my word, it does. Okay? So, what we do in this case is we divide mean squared A and mean squared B by mean squared AB. Because we can isolate alpha or beta by dividing, say, alpha plus alpha beta plus epsilon by alpha beta plus epsilon. Oh, that's called an error term. It's what you divide by an analysis of variance. It's called an error term. We have an error term for A and B, so we're okay. But we divide mean squared AB by mean squared. Okay? Do you understand what I'm saying here? Does that make sense? So that's if we've randomly chosen all the levels. What if we, probably figured out what the third option is here. What if we randomly chose one set of levels and the other ones were fixed? So, A is fixed, in this case, and B is random. So if A is fixed and B is random, or B is fixed and A is random, but in the example we give you, A is fixed and B is random, we have what's called a mixed model. And the expected values work out like this. So for A, it's alpha plus alpha beta plus epsilon. For B, it's beta plus epsilon. For the interaction, it's still alpha beta plus epsilon. And for the mean squared error, mean squared deviation, if you want to call it that, it's mean squared, it's epsilon. And that is not a typo. And every year someone says to me, doesn't that go the other way? And the answer is no, it does not. Why? Because math. Let's just leave it at that. If you want, I can bring in a couple of really high-level textbooks and show it to you. Or you could just believe me. Just believe me is probably a good idea, because because those proofs in those graduate level textbooks that I had when I was a graduate school, my prof kept saying, you don't have to worry about the proofs. Well, there's statisticians. To do proof. Also, learn matrix algebra for next week. That was one of the things that happened as my PhD read stats. Anybody hear a lot of matrix algebra? We're all like, no. Well, learn it by next week. Okay. So I know this looks weird and wrong and it's counterintuitive, but it's actually correct, okay? Even though A is the fixed factor, B is the random factor, we divide mean squared A by the interaction of mean squared B by good old mean squared error. This is an amazing. It was so hot during the last class, I could hardly drink the coffee was in it. And now it's almost temperature, right temperature. Coffee today, 4 hours of sleep. I know you don't care. Bunch of uncaring, horrible people, but I can. I'm sure you all care a great deal about my sleep habits, but it's weird. I was like, oh, that's right. Like, I didn't don't teach on Mondays. It was like the term was starting again. I was nervous. It's the only explanation. That night, I'd have a pizza at like 11 o'clock. It's probably not actually more likely. Because I'm an idiot. The whole time I'm hungry, right? So it's like, oh, it's leftover pizza. I'll eat some pizza. And I'm thinking, this is probably a really big mistake. And it was. Okay, now, we're assuming with a random effects model that the levels are randomly chosen. And like I said, when would you do this? I don't know. The example I like is this idea of, let's say you were looking at tire wear. And that's an odd thing to say, but this is an example I kind of like this. Let's say you're looking at winter tire wear in Canada, right? And you're doing this not because it's scientifically interesting. You're doing it because you work for Goodyear or somebody. And you've got different rubber compounds. And those are the only two you're interested in, compound A, let's not say A and B. Compound 1 and compound 2. And that's your fixed effect. Okay? Because you just have those two. But then can we go to everywhere in Canada? Well, no. We could, however, say we want a certain number of, we want a pool of cities, and we'll test these tires in a bunch of different cities, and we'll randomly choose them. And then we can look at the relative of those cities and all that later. That makes some sense to me. You actually have randomly chosen all these cities of, let's say, more than 20,000 people in Canada. Okay? That's kind of sensible. And in that case, you would randomly choose your levels. I always do this with randomly choosing, like I'm actually choosing. What are we usually doing? We're doing a sort of kind of not really random effects, not really kind of sort of model, which is a technical term. But unless you actually chose your levels randomly, the best approximation is a fixed effects model. So while at the beginning I said you can't do this, you actually can. So the math is closest to a fixed effects model when we do what we typically do. So when I say we'll have 1 hour and 7 days as the two retention intervals, and I didn't pick those randomly, and I am really interested in what's in the middle, and I'm going to infer it anyway, the closest thing to that is really a fixed effects model. Mathematically. Very rare, unless you actually chose your levels randomly, okay, don't use a random effects model. I have once in my career seen a paper that it came across my desk kind of thing, like so something I reviewed for a journal or something I read or an honors thesis, and I believe it was an honors thesis project where they used a random effects model. Or I was told that they should use a random effects model. Because most people don't even know about this. Not like this is secret knowledge or something. But most people don't even think about this because it's just not something we tend to do. And like I said, you might do it if you really like field work and you had access to maybe, like if you really like field biology kind of work, like so you're doing stuff like that Jen does, for example, looking at bird song, that kind of thing. But still, it's not like she can have access to 25 different sites and just choose 3 of them. It just doesn't work that way. You're never going to have access to that much. If you do, you take data everywhere, right? So it's not really something that comes up a lot unless you're applying something, typically. Like I said, the tire example is actually a good one. Questions? Any questions for me at all? Okay. So that's the thing. Did you actually randomly select your levels? If you randomly selected your levels, you're fine. Use the random effect or mixed model, whatever. But if you didn't, just stick with this fixed effects model that actually does the best job. And again, how do we know this simulation? It's just Monte Carlo simulations. And I don't know, there's apparently nothing left to say there. Okay. So we have an ANOVA summary table. And it just gets a little bit bigger now than the one for the one-way analysis of variance, or the simple analysis of variance, which looks like this. And you've got the sources of variation, A, B, A by B, and error. Degrees of freedom are A minus 1, B minus 1, A minus 1 times B minus 1, and AB times N minus 1. And then you take the sum of square, divide by its requisite degrees of freedom. Okay? Okay. Now again, that's only for fixed effects, but it's going to be fixed effects. The chance that any of you will ever, if you go on into the field and use random effects model is really small. You might someday, but I mean, it's so, like I said, I've seen it once in my life. In the kind of stuff that I'm interested in. So, on a test or a quiz or whatever, you can assume that it's fixed effects. Unless I tell you it's not fixed effects, it's fixed effects. I'm just telling you about this because it's something that, well, there's a couple of reasons. There's a really good reason that goes into when we talk about something else later in the course. But it's also the case that, I think it's something you should know. Even if you're never going to run into it. All right, questions so far? Oh my God. Now it's a 2 by 2 by 2. You don't have to just have 2 independent variables, but put 3 independent variables, A, B, and C. And you're thinking, Dave, what kind of, this is crazy. What do you mean 3 independent variables? How could an experiment be that complicated? There are 2 different attention intervals, 2 different kinds of stimuli, 2 different species of birds. Done. Of the 7 experiments in my PhD dissertation, 6 of them had 3 independent variables. Now, on the other hand, if you want to do your honors thesis with me, I won't let you do this. Even if you come to me and say, I've got these like 3 different, no. You will have 2 at the most. Because it gets hard. When you're used to doing this, it's easy. But when your first time doing independent science, I want to do something complicated. So we can say, no, you don't. I won't let you. And most of us are on that same place. Because, why make your life difficult? The first thing I usually end up saying to my honors students is, this is not a PhD dissertation. Please calm down. All right. So we have here, though, we have 8 groups now. It's a 2 by 2 by 2. Okay. So now we have 3 main effects, A, B, and C. We have 3 two-way interactions, AB, AC, and BC, and a 3-way interaction, ABC. A 3-way interaction is when a 2-way interaction changes depending upon some level of a third variable. Did your phone just blink or something? Yeah, okay, good. I thought maybe perhaps I was having a stroke, so I'm glad I Dr. Penfield, I smell burnt toast. That's really only for me, apparently, but nonetheless. Okay, so we got 2-way interactions and a 3-way interaction and 3 main effects. And like I said, this isn't, when you look at me, you go, Jesus, complicated. When you put it into, like if we had a cognitive task, oh, let's make it something spatial. So, I don't know. Oh, I know. Mental rotation. You know what that is? You know mental rotation? When I show you a letter, if there's any chalk in this godforsaken hellhole of a classroom, there isn't? Well, that's just grand. There's a marker, which is completely useless. There's no chalk. Oh, I found some. So, I show you a letter, like that. And I ask you, is that a letter? Okay. Now, what you have to do that is you have to actually rotate it in your head until it's right way up. Because if I ask you if that's a letter, that's not a letter, it's a backwards R. Maybe it's a letter in Russian or something. It's not a letter with our alphabet. You're supposed to rotate it in your head, and the cool thing is, the really cool thing about this is the number of degrees you have to rotate it is proportional to your reaction time. Nobody gets them wrong, by the way. It's just all about reaction time. It's a really cool result. It's very reliable. And there's some really cool, interesting things here too, because there's a reliable, very small but reliable sex difference between men and women. Okay, men are better at this than women on average. I couldn't say a pick. I couldn't say if I had Matt and Shannon, and I said, okay, you two guys, and I'll pick you. No, it wouldn't work. But if we took, how many people do we have here? 1, 2, 3, 4 guys. It would be, I know we can find the effect with just the men and women in this classroom. It's meaningless, okay? So it's not something that's like, and therefore women shouldn't be allowed to drive cars. That's not what I'm saying, but it's a small but significant effect, okay? There's also something weird going on with handedness. That it's more pronounced, I gotta see if I remember this properly, in the right-handed people than the left-handed people. Like it's easier for right-handed people than left-handed people, that's correct. But only if you're a guy. Whoa. I think I'm remembering that properly. Now, what's a third possible variable we can throw in? I don't know, are you drunk or not? Okay, so let's throw in that. So you've had 0 drinks or 5 drinks. Now you can see where there could be a 3-way interaction, right? Where maybe the alcohol and handedness go together along with your sex and screw up your ability to maybe get rid of any difference. Because, this kind of thing. So it's certainly possible to imagine research designs that have 3 different variables. It's not like it's some magic thing. And like I said, when you give an example, it's not so bad rather than just A's, B's, and C's. Oh yeah, you know what? I do have a picture, I think, later. Now the structural model of this is x equals mu plus alpha plus beta plus gamma plus alpha beta plus alpha gamma plus alpha beta gamma plus epsilon. I've said that before. It's just A, B, C, A, B, A, C, B, C, A, B, C. There. There is no C. The third letter of the Greek alphabet is gamma. And our alphabet comes from the Greek alphabet. So you're saying, why is there G there? Why is it? Because I literally just learned what was happening. When the K sound drifted and became a G sound, and that sound started to show up in Latin, they had to invent a new letter. So they took a C and put a little thing on it to make a G. That's really good. Cool, right? The things I learned listening to the History of the English Language podcast. When I listen to what I'm shoveling the driveway. I'm doing a lot of this, I stop. That's cool. Okay, so A, B, C, A, B, A, C, B, C, A, B, C. Okay? It would look something like this. Now, this is an example of a three-way interaction. So this is, no, we have an AB interaction at C1 and an AB interaction at C2, but they look different from each other. The interaction, the two-way interactions change depending upon the level of a third variable. That third variable in this case, of course, is C. Okay? Does that make sense? It's not so bad, right? And you'll see graphs presented like this in papers all the time. I know a lot of you are writing essays and stuff. It's getting close to that time of year when you start to write papers. And you'll see this kind of thing. Okay. So these kind of designs are actually great because they allow you to look for these interaction effects. A lot of what we study in like life sciences in general, right? So in biology, psychology, we're looking at complicated living things. These are complicated living systems we're interested in. And because of that, we don't usually see simple effects of one variable on a system. You can isolate them, that's great, and you can do that with this as well, with these designs. But we're also usually interested in, how do 2 or 3 or 5 variables come together? In fact, a lot of our theories about, memory. There are different kinds of memory. Okay, so there's implicit memory and explicit memory, and levels of processing affects one and not the other. Retention interval affects one and not the other. Or you talk about, say, semantic and episodic, whatever. We a lot of times look for, in psychology, a lot of times we end up looking for what are called associations between two variables in things like memory. So we can say, they must be different systems if variables affect one and not the other. That's what an interaction is. Right? That's what an interaction actually is. It's just one of these dissociations.